Okay, so the last video I did a little bit abruptly. That's because I had forgotten to delete things off of my camera, so the memory card was full. I had pretty much finished with that phase portrait. And believe it or not, I do actually reshoot these videos if I notice a mistake at the time I'm making them. And that was like take 4 or 5 of that one, so I didn't want to redo it. Just want to point out that with the last example, because we were able to draw the level curves for our Hamiltonian function, we were able to get a good sense of what the phase portrait looked like. And it was pretty clear from that, I think, that the origin was a saddle. We could, if we wanted to, linearize the system at the origin and confirm that we do get a saddle. Okay. All of the other equilibrium points were points that we couldn't classify because they were not isolated points. Okay. What I want to do now is take a look at this system that we have right here. This is presented in your book, but it's presented very early on in section 5.3. So before they fully defined what it means to be Hamiltonian, how you check, how you find a Hamiltonian function. This is sort of the book's motivating example. And so they sort of say, oh, here's this function that's conserved on the solution curves. And they just sort of present it from thin air, which is totally fine, because that's what they're trying to do, is just give a motivating example and then delve deeper into how this works and what conditions make it work and all of that. So I just want to take this as if we're doing it from scratch. I want to first of all verify that it's Hamiltonian, then find a Hamiltonian function. Okay. Turns out when we find that, it's going to be a little bit harder to actually draw the level curves because it's not going to lead to a familiar function whose graph I already know. So in this case, what I'm going to do instead is find my equilibrium points and try to classify them by linearizing the system and see what that tells me. And once we've gotten all that we can, then we'll cheat and we'll look at the phase portrait that's given in the book because something kind of interesting happens. Okay, so I want to remember that if a system is Hamiltonian, that's because there exists a function h such that dh by dt is 0 if I plug in points on the curve, so that the function h, which is a function of x and y, is constant on my solution curves. But this would be the partial of h with respect to x times dx by dt plus the partial of h with respect to y times dy by dt. And I'm hoping that's going to be 0. I like to write this out because it helps me to remember what needs to be what. Okay. Basically, this is getting multiplied by the partial of h with respect to x. That's getting multiplied by the partial of h with respect to y. Cheap way to make this 0 is to make this the opposite of that. In fact, we kind of have to do that to make it 0. A way to do that is to let this be the partial of h with respect to y, and this be the partial of h with respect, the opposite of the partial of h with respect to x. If that's true, this will be 0. So that's what we're checking for. If a system is Hamiltonian, dx by dt will be the partial of some function h with respect to y. dy by dt will be the opposite of the partial of that same function with respect to x. So in order to check to see whether or not this is Hamiltonian, what I need to do is get to the second partials, in particular the mixed ones. So I'm going to take a look at the partial of f with respect to x. Because if this is Hamiltonian, that's already a partial with respect to y, and so this would give me a mixed partial of h. And that's just going to be a lovely 0. Then I'm going to take a look at the partial of g with respect to y. Because if it's Hamiltonian, this is already the opposite of the partial of h with respect to x. So when I take the partial with respect to y, I'm going to get the opposite of the other mixed second partial. Okay. Now, when I take the partial with respect to y, I just get 0. Now, in this case, these guys are the same. In general, what I'm looking for is that the partial of f with respect to x is the opposite of the partial of g with respect to y. That's because this is a mixed partial. This is the opposite of a mixed partial of h if it's Hamiltonian. Okay. But that is certainly satisfied, so this is in fact Hamiltonian. Okay. So we have confirmed that our function is Hamiltonian, and so now I can say I know that this is the partial of h with respect to y, and I know that this is the opposite of the partial of h with respect to x. So if I want to find my Hamiltonian function, I'm going to start by just integrating this with respect to y. So step one, I'm going to say h is an antiderivative of the partial of h with respect to y dy. That's going to be an antiderivative of y dy, which is just y squared over 2 plus k of x. Don't forget, when we're integrating with respect to y, we're holding x and all functions of x constant, so my constant of integration isn't necessarily a straightforward constant, it's some function of x. Okay, so now I'm going to take the partial with respect to x of h. So when I take the partial of this part, it drops out, but I'm going to just get k prime of x. But I can now set that equal to the opposite of g of xy, which would just be x squared minus x. When I take the opposite, the x becomes negative and the x squared becomes positive. I just switched the order to write the positive piece first. So, step 3, I can say k of x is going to be an antiderivative of k prime of x, which is going to be an antiderivative of x squared minus x, which is going to be x cubed over 3 minus x squared over 2, plus an actual honest-to-goodness constant. And if I just want to have a Hamiltonian function for this system, I can choose to make c equal to 0. So then I can put the pieces together. That would be step 4, but I'm going to just jump up here to do that. I can say h of xy is going to be, put the pieces together, so we're going to get y squared over 2 plus x cubed over 3 minus x squared over 2. And so my solutions are the level curves for this function. So that would be y squared over 2 plus x cubed over 3 minus x squared over 2 equals k for some constant k. So, very nice. We have successfully found our Hamiltonian function. Now, I don't off the top of my head know what curves like that look like. That's not one of those curves in 2 space that I'm super familiar with. Okay. And so I could play around with things. I could solve for y. It would be one of 2 functions of x involving the square root. I could take a bunch of derivatives to take a look at solution curves, but that seems kind of tedious. I could use some technology to get that, or I could observe that this example was in our textbook and we've got the phase portrait there. So I'm going to keep that on reserve and we'll cheat and look at the textbook in just a little bit. But what I want to do before that is just see if we can take a look at our equilibrium solutions and classify them, because that's work that we should definitely be able to accomplish. So if I want an equilibrium solution, I know that dx by dt has to be 0 and dy by dt has to equal 0. So if dx by dt is 0, y is 0. If dy by dt is 0, x minus x squared is 0. So that's x times 1 minus x is 0. So x is 0 or x is 1. So this particular system has exactly 2 equilibrium solutions, 0, 0, and 1, 0. So let's see if we can linearize the system at each of these equilibrium solutions and then classify those to get some information about the phase portrait. Then we'll take a look at the phase portrait that's given to us in the text and confirm that what we found is consistent with what we're given in the text. Okay, so that's where we will pick up in the next video. See you then.